Okay, I think my YouTube is up. Okay, so as I was saying, the last time we were here, we were looking at this problem right here, all right? And if you recall, this is a combustion analysis type problem where you're given a certain amount of a particular substance which contains, in this case, carbon, hydrogen, and oxygen. You burn it, you collect the products of the reaction when it's burnt, carbon dioxide and water. You determine their masses, and based on the masses, we could determine the masses of the carbon, hydrogen, and oxygen present in the compound. And then we determine the empirical formula, all right? So we went through this exercise last time. And I remember saying that there was another problem I was hoping to have, which would show us how to use the same data along with some other information to determine the molecular formula for a compound. So the example we're going to look at is this one right here. I basically went online searching for different examples, and I think this one is a very good example of the type of problem that I was mentioning, where you're given the mass of the compound. In this case, the compound is caffeine. In fact, let me do this. Let me copy and paste this into a PowerPoint slide. Okay, so that's the question. Let me get rid of this. Let me move this up here. And then let me make this a bit larger in terms of the font. I think 24 is enough. Okay, so this is the question. Move this out of the way. Where am I going to put this? Hold on. Let me get, oh shoot, what did I do? Let me move this down a bit. And then let me go back to this again. Let me move this up. Okay, so this is a question. It gives you that caffeine, which of course we're all familiar with. It's a stimulant that is found in different beverages, coffee, tea, etc. Contains carbon, hydrogen, oxygen, and nitrogen. So in this case, there are three elements we have to contend with, all right? So they say that combustion of 1.000 milligram of caffeine produces this amount of carbon dioxide, this amount of water, and this amount of nitrogen. And the question gives you the molar mass of caffeine, which is this, which is the additional information that you're going to need. We're going to see why that is important shortly. And therefore, the question is asking, what is the molecular formula of caffeine? Okay, so the first part of tackling this problem is similar to what we did the last time. So basically, we're going to need to first start off with the 1.813 grams of CO2, and we're going to find out the mass of carbon present in this mass of carbon dioxide. So we have to multiply that by, well, first, this is milligrams. So this should be milligrams. So the first thing I would do is convert this to grams. So I'm going to put 1,000 milligrams down here of CO2 and 1 gram of CO2 above. And then we're going to convert from grams of carbon dioxide to moles of carbon dioxide. So we're going to put 1 mole of CO2 above, and down here the molar mass of carbon dioxide, which is 44.01 grams of CO2. All right. Then the next step is where we convert from moles of carbon dioxide to moles of carbon. And based on the formula, that would be a 1-to-1 mole ratio. And then the last step in this process is where we convert from moles of carbon to grams of carbon. And let me do this. Let me get my eraser. And then go back to, Okay, what am I doing wrong here? Hold on 1 minute. Okay, how do I get back my pen? Oh, here. Okay. All right. So this should be actually let me get my erase again. I'm sorry about this, folks. So let me erase this top part here. Okay, and then let me get back my pen function. Okay, so the molar mass of carbon, of course, is 12.01 grams of carbon. And down here, you're going to have 1 mole of carbon, all right? So let me get my calculator and work this out. 1.813 divided by 1,000. Oh, 1.813 divided by 1,000. Then I multiply or divide by 44.01, multiplied by 12.01. Okay, so according to my calculations, this works out to be equal to 4.9, let me see here, 468. So this should be 4.948 times 10 to the minus 4, and this would be grams of carbon. And then I'm going to do a similar calculation for the water. So that would be 0.4639 milligrams of water. We're going to convert that to grams. So we're going to have 1,000 milligrams of water down here, 1 gram of H2O down here. This should be H2O down here. And then here, we're going to convert from 1 mole of water above here, and the molar mass of water will be down here, which will be 18.02 grams of H2O, all right? So we're converting from grams to moles of water. And then the next step, if you remember, I keep stressing in this step here that the ratio between the moles of water and moles of hydrogen is 2 to 1. 2 moles of hydrogen to 1 mole of H2O, all right? Very important. And then the next step, final step in this line, is where we have 1 mole of hydrogen down here, and up here we have the molar mass of hydrogen, which is 1.008 grams of hydrogen. And we work that out. So when we work that out, we're going to get 0.4639 divided by 1,000 divided by 18.02 times 2 times 1.008. All right. And according to my calculations, this works out to give 5.1, let me see here, 5.154 times 10 to the minus 5 grams of hydrogen. All right, so we have found the mass of carbon and hydrogen. And we also have the mass of nitrogen, because according to the question right here, the mass of nitrogen is 0.2885 milligrams of N2. So to deal with that, we're going to put 0.2885 grams of nitrogen. We're going to convert that from, let me see here, from, well, this should be milligrams, okay? So basically to make things shorter, I won't go through any unnecessary steps. We know that 1,000 milligrams of nitrogen is equal to 1 grams of N2, all right? So therefore this becomes 0.2885 divided by 1,000. So that gives you 2.885 times 10 to the minus 4.
I have a question when you get a chance.
Yeah, sure. 2.885 times 10 to the minus 4 milligrams of nitrogen. I'm sorry, grams of nitrogen. Okay, yes, what's your question?
When you were solving for H2O, you got 5.154.
That's what I did. I don't know, I could be wrong, but that's what I got.
Okay, I got, 5.1899.
Okay, let me try it again. So 0.4639 divided by 1,000 equals that divided by 18.02 times 2 times 1.008. Okay, yes, you're right. So let me change this here. The 5.18, 5.1, so 4 sig figs, that will be 0.190. All right, when rounded off to 4 sig figs. Okay, so thank you very much for making that correction. And that's the reason why I keep telling you guys that, you know, make sure that you work along with me so that I'm on the right track. Okay, so here we have 2.885 grams times 10 to the minus 4 grams of nitrogen, right? And it doesn't matter if it's nitrogen as N or N2, this would be the mass of nitrogen present in the compound, right? So this would be equal to 2.885 grams of N, all right? So we have determined the masses of carbon, hydrogen, and nitrogen. The only other element that remains is oxygen, right? Because remember, oxygen is listed as one of the 4 elements. Hold on. Oh, shoot. Okay. So this is oxygen here. So we need to determine the mass of oxygen. And I'm running out of space. So let me go to my tablet here. So how do we get the mass of oxygen? Well, to get the mass of oxygen, what we have to do is add the masses of the carbon. So let me see if I can write that here. The mass of the carbon, well, the mass of the compound itself is 0.1000 grams. So 0.1000 grams. We subtract from that the mass of carbon, which is 4.948 times 10 to the minus 4 grams, plus the mass of the carbon, which is 5.190 times 10 to the minus 5 grams, plus the mass of the nitrogen, which is 2.885 times 10 to the minus 4 grams. All right. So let me just make a correction here. This should be times 10 to the minus 4. All right. Okay. So going back to this right here, we need to work this out. So let me do that now. So I'll work out what's within the parentheses first. 4.948 times 10 to the minus 4 plus 5.190 times 10 to the minus 5 plus, okay, I did something wrong with my calculator, so I need to start over. 4.948 times 10 to the minus 4 plus 5.19 times 10 to the minus 5 plus 2.885 times 10 to the minus 5 equal. Okay, and then I subtract that from 0.1000 and, oh, interesting. Okay, something is not working out here because when I subtract all of this from 0.1, I got 0. Let me see here. They're saying that it has, well, based on my calculation, it has 0 oxygen. So something is wrong with this problem here. Let me try this again. 4.948 times 10 to the minus 4 plus 5.19 times 10 to the minus 5 plus 2.885 times 10 to the minus 5, and then 0.100. Okay, so now I got a different number. The number I got here is 0.0994 grams. So this will represent the mass of oxygen. This represents the mass of carbon. This is hydrogen. This is nitrogen. And we have the mass of oxygen. So the next step is
you were supposed to subtract all that from 1,000?
From 0.100, well, 1,000 milligrams, which is 0.100 0 grams.
Okay.
Yeah. Right. I skipped that step. Basically, I convert the milligrams to grams for the mass of the entire compound. All right. Okay. So the next step is, as we did before, we set up our table: carbon, hydrogen, oxygen, and nitrogen. Right. And let me just move this up here, create some space. So the first row will contain the masses of all these compounds or all these elements. So this will be 4.948 times 10 to the minus 4 grams. For hydrogen, it's going to be 5.190 times 10 to the minus 5 grams. For the oxygen, it's going to be 0.0994 grams. And finally, for the nitrogen, it's going to be 2.885 times 10 to the minus 5 grams. All right. So those are the masses, right? And then let me make sure I've written all these correctly before I erase this down here. 0.0994 grams for the oxygen and 2.88. Okay, good. So what I'm going to do to create some space is erase this down here. And then I'm going to write down this row for the moles. And if you remember what we did the last time, we simply take the mass of each of these and multiply by or divide by their respective molar masses. In the case of carbon, that would be 12.01 grams per mole. In the case of hydrogen, we divide the 5.190 times 10 to the minus 5 grams by 1 mole over 1.008 grams. And then in the case of oxygen, it would be 0.0994 grams multiplied by 1 mole over 16.00 grams. And then finally, in the case of nitrogen, 2.885 times 10 to the minus 6 grams multiplied by 1 mole over the molar mass of nitrogen, which is 14.01 grams. And then we calculate each of these. So let me do this one firstly. 4.948 times 10 to the minus 4 divided by 12.01. And according to my calculations, this works out to be equal to 4.1, 460, so 4.120 times 10 to the minus 5 moles. And then for hydrogen, it's 5.190 times 10 to the minus 5 divided by 1.008. And according to my calculations, this works out to be equal to 5.148 times 10 to the minus 5 moles. And then in the case of oxygen, it's going to be 0.0994 divided by 16 equals, okay, so this gives me 6.213 times 10 to the minus 3 moles. And then finally, in the case of, okay, I think I made a mistake here. This should be minus 5. So 2.885 times 10 to the minus 5 in the case of nitrogen divided by 14.01. And according to my calculations, this works out to be equal to 2.059 times 10 to the minus 6. So these are all the mole values for these different elements. So let's go to the next step. And can somebody remind me what the next step should be?
Dividing by your lowest value.
Exactly. So which of these would be the lowest?
nitrogen?
Yes, I would agree with that. So we divide right through by 2.059 times 10 to the minus 6. So when I do that for the carbon, 4.120 times 10 to the minus 5 divided by 2.059 times 10 to the minus 6. According to my calculation, this works out to be 20.01. In the case of hydrogen, it's 5.148 times 10 to the minus 5 divided by 2.059 times 10 to the minus 6 equals, and according to my calculation, this works out to be 25.002. And then in the case of oxygen, it's 6.213 times 10 to the minus 3 divided by 2.059 times 10 to the minus 6. And wow, okay, something is wrong here. This is a very huge number which seems out of place. I have 3,017. That does not look right at all. Let me try for nitrogen, 2.05. Oh, well, that would give you 1. So this would be 1, but I have a question mark for this one here. And let me see here. I'm wondering where the error occurred. Let me see here. Not there. Let me try this again. 1, 2. Okay, I see the problem. The problem is that I made a mistake of saying that 1.00 milligrams is equal to 0.100 grams. It should be 1. Hold on, let me see. 1.00. 1, 2. It should be 1 gram. I should have subtracted all of them from 1 gram. Okay, sorry about that. So what I'm going to do is go back to where? Go back to. Okay, let me go back to here. Let me see if I can solve that problem down here. So what I should have done is 1.000 grams minus 4.948 times 10 to the minus 4 plus 5.19 times 10 to the minus 5. And these are all grams. Plus 2.885 times 10 to the minus 5. Okay, so let me take care of this part here within the parentheses. So that should be 4.948 times 10 to the minus 4. Whoops, let me do this again. 4.948 times 10 to the minus 4 plus 5.19 times 10 to the minus 5 plus 2.885 times 10 to the minus 5, and then subtract that from 1. Okay. Times 10 to the minus 4 plus 5.19 times 10 to the minus 5. Plus 2.885 times 10 to the minus 5. Okay, what's going on here? 4.948 times 10 to the minus 4 plus 5.19 times 10 to the minus 5 plus 2.885 times 10 to the minus 5. And then when I add that, when I subtract that, Let me see here. Okay, so let me see here. 1 minus 5.736 times 10 to the minus 4. Okay, something is wrong here. I'm going to abandon trying to solve this problem for the time being because the numbers are not working out right. And that's what happens when you pull some problems from the web. I should have tried this problem before I started class, but I was kind of in a hurry this morning. Anyway, what I'm going to do is I'm going to revisit this problem, or I'll try another problem and get back to you guys with another example, because I think it's really important that you guys understand how to get the empirical formula from the molecular formula. So I'm going to abandon this for now. I apologize for that, folks. And what I'm just going to do is continue with the rest of our lecture today. All right, so the next thing we're going to talk about here is stoichiometry, which is basically what this chapter is all about, but we're going to get into what stoichiometry is actually about in this section. So we know that in any chemical reaction, basically it comes down to identifying what the reactants are and what the products are. And we can represent it using a mathematical equation where we have the reactants typically on the left side and the products typically on the right side, all right? So when you're writing a chemical equation, of course, you're going to use the chemical formulas representing the different substances involved as reactants or products. And in addition to the chemical symbols, we use some other symbolism, such as a plus sign, which is used to separate the symbols for the reactants and products on either side of the equation. We use the arrow to indicate that at the beginning of the arrow, you'll have the reactants and the products will be on the other side. So basically the arrow typically points from left to right, where the products will be on the left, and the reactants will be on the left and the products will be on the right. Okay, so there are some other symbols you see as well, such as the ones that you see here on the screen. So you have G for gas, L for liquid, S for solid, and AQ for aqueous solutions, right? So these basically indicates the state of the substances involved in the reaction. You may see some other additional information, such as a small triangle, which represent heat. And in other cases, you might actually see the actual temperature being used, and also other conditions, actual pressure, temperature, and so on and so forth, all right? So let's get into how we actually write a balanced equation. So here we have an equation representing the formation of water. And again, this is something that you would have encountered in your previous chemistry experience. So we have the symbols for hydrogen and oxygen on the left side and water on the right side. Now, if you are to use an equation to accurately represent what is happening in a reaction, then the law of conservation of mass must be obeyed. If you remember, that law basically says that the total mass is conserved when a reaction takes place. Another way of stating it is that the total mass of the products will be equal to the total mass of the reactants. So the equation must be balanced to reflect that fact. And in fact, what the equation, in order to balance the equation, what you have to ensure is that the number of atoms of each element are the same on either side. So you have to make some modifications to the unbalanced equation in order to achieve this. So if you look at the equation that we started off with, you'll see that whereas the hydrogens are balanced, you have 2 hydrogens on either side, the oxygens are not balanced because you have 2 oxygens on the left and 1 oxygen on the right, all right? So we need to somehow achieve a balance of the oxygens, all right? So the question now becomes, how do we achieve this balance, all right? Well, what we need to do whenever we're balancing equations is that we have to make changes to the coefficients or the whole numbers in the balance equation so as to ensure that everything is balanced, that all the atoms are the same on both sides for each element, all right? So that's the modification that you need to make. You cannot make changes to any other numbers. For example, you should not make any changes to the subscripts involved in the reaction, all right? So we're gonna see some examples of the incorrect way of doing it and the correct way of balancing. So if you look at this here, you'll see that in this case here, what this person did, whoever did this person just simply add an oxygen here to achieve the balance of oxygen. That is incorrect. You cannot do that. You cannot add oxygens or any other element for that matter, just arbitrarily like that, all right? What another person did here is that they changed the formula of H2O to H2O2 by adding an oxygen to that formula. Again, that's not correct. You cannot just simply create a compound by adding elements to it in order to achieve the balance of all the atoms. So the correct way of doing it, as I said before, is making changes, the appropriate changes to the coefficients involved in the reaction or in the equation. And as you can see here in this last example, what this person did was add a coefficient of 2 here and a coefficient of 2 here, right? And in so doing, now we have a balance because we have 4 hydrogens on this side, 4 hydrogens on this side, 2 oxygens on this side, and this 2 here multiplied this oxygen by 2. So therefore now we have a correctly balanced equation. All right, so that's basically what you need to do in order to balance an equation. You make changes to the coefficients. Don't make any changes to the subscripts. You do not just simply add arbitrary elements to either side in order to achieve balances, to achieve a balance. Okay, and you'll get some examples, or I should say an exercise where you can get your practice in terms of balancing equations. Okay, so now that we know how to balance equations, we're going to talk about next what we call the stoichiometric equivalence. Now, and going back to the equation for balancing, the balance equation for the formation of water, which I'm going to rewrite up here. Okay, what's going on here? So I'm going to write 2H2O to form 2H2 plus O2, all right? So that's a balance equation we were looking at. Now, based on this balance equation, we can get some information about this reaction in terms of the proportional relationship between the different substances involved. So for example, you can see that there's a coefficient of 2 here for the H2O, and there's understood that a coefficient of 1 here is for the oxygen. So there's a 2-to-1 ratio in terms of the number of molecules of oxygen and, I'm sorry, between the molecules of water and oxygen. So therefore we can express that as an equivalence as shown here, 2 moles of hydrogen to 1 mole of oxygen. Similarly, we can write down a relationship between water and hydrogen, which would be 2 to 2. And we can write down a relationship between the hydrogen and the oxygen, which would be, well, actually, this should be 1 to 2 right here. This should be 2, all right? So please make a note of that, all right? So basically, we can express each of these equivalences as fractions, all right? So we can say that, for example, the mole ratio between the hydrogen and oxygen can be expressed as this conversion factor right here. 2 moles of hydrogen to 1 mole of oxygen, or 1 mole of oxygen to 2 moles of hydrogen, all right? And we can see that we have similar relationships here and here for 2 other relationships, all right? So the reason why I'm pointing this out is because these conversion factors can be useful in problem solving. So if you're given a certain amount of a substance, you can actually use this kind of relationship to determine the amount of the other substance involved, either as a product or a reactant. And you'll be doing a lot of these types of calculations when you are doing or solving stoichiometric problems. Okay, so let me give a simple example of this so that you can get a feel for, okay, what's going on with the pointer here. It's very hard to see the pointer. Okay, now I see it. All right, so let me go to this right here, and let me create another slide. And let's say, okay, so let's say you have, I'm just going to make up a problem here. So let's say you have a reaction of nitrogen plus hydrogen to form ammonia, all right, NH3, okay? And of course, we need to balance this equation. So to balance it, we're going to need a 2 here and we're going to need a 3 here, all right? And let's say that you're starting off with 2.79 grams of nitrogen, and let's say you're trying to determine the mass of ammonia that would be formed, all right? So what you'll do is start off with the 2.79 grams of nitrogen, and then I'm going to convert that to moles. So you're going to have 1 mole of nitrogen down here, and the molar mass of nitrogen down here would be 2 times 14.01, which would be 28.02 grams of nitrogen, all right? So we would have converted from grams of nitrogen to moles in the first step. In the next step is where you look at the moles of nitrogen and compare it to the moles of ammonia, right? Sorry, moles of ammonia. And as you can see, there's a 2-to-1 mole ratio between the two. So you're going to have 2 moles of NH3 down here, 1 mole of N2 down here, right? So now we would have calculated the moles of ammonia up to this point. But we can't stop there because the question is asking for the mass of ammonia. So the next step is where we do that. And that's where the molar mass of nitrogen, the molar mass of ammonia comes in. 1 mole of ammonia would be down here. And the molar mass of nitrogen would be, I know it's 17 point something, but I want to get the accurate number. Nitrogen is 14.01 plus 3 times the molar mass of hydrogen, which is 1.008. So 17.03, 17.03 grams of NH3 would be the molar mass. Okay, so all we have to do now is the number crunching. 2.79 divided by 28.02 times 2 times 17.03. And according to my calculations, this is going to be equal to 3.39 grams of ammonia. So this is a typical stoichiometric type problem, all right? So as you can see in this particular example, I went from grams of nitrogen to moles of nitrogen, and then from moles of nitrogen to moles of ammonia, and then from moles of ammonia to grams of ammonia. All right, that's basically the pathway I followed in order to get to what the question is asking for. All right. Okay, any questions about this example? Any questions? Okay, so, excuse me. So let me go back to this right here. So now that we have completed the topic of stoichiometry, now we're going to talk about this whole concept of limiting reactants, all right? And basically, this whole concept deals with a situation where if you have a certain amount of different reactants involved in a reaction, which one will be the one that will determine the product outcome if the amounts of the reactants are not stoichiometrically equivalent, all right? So to illustrate this, we're going to look at this non-chemistry example. Let's say you're given a task of preparing meals for a picnic, for example. And in order to make one package meal, right, which consists of a sandwich, 2 cookies, and an orange, right? So that's basically the equation that you're going to use in order to form or produce 1 unit of a packaged meal. You're going to need 1 sandwich, 2 cookies, and 1 orange, all right? So we can represent this in the form of a chemical equation, even though this is not really a chemistry example, all right? So if that's the case, then what would be the outcome if you have at hand 11 sandwiches, 16 cookies, and 10 oranges, all right? Now, based on the above equation here, if you look at things from the standpoint of the cookies, right, or I should say of the sandwich, if you look at the standpoint from the sandwich perspective, for each sandwich, based on this equation, you're going to need 22 cookies. But we do not have 22 cookies. We have only 16, right? So therefore, all the sandwiches will not be used up. All the 11 sandwiches will not be used up, all right? Now, if you look at things from the standpoint of the oranges, right, based on this equation, for 10 oranges, you're going to need 20 cookies. Again, you don't have enough cookies, so therefore, not all the oranges will be used up as a result. Now, if you look at things from the standpoint of the cookies, right, you'll see that for 16 cookies, you're going to need 8 sandwiches and 8 oranges, right? So therefore, all the cookies will be used up. You're going to have some sandwiches left over. Actually, you're going to have 3 sandwiches left over because 8 of them will be used up. And here, 8 of the 10 oranges will be used up. So you'll be left with 2 oranges, right? So in this non-chemistry example, the cookies would be the quote unquote limiting reactant or limiting item, right? Because it is the cookies based on the amounts available of each of them. The cookies would be the ones that would limit the amount of product you're going to get. So therefore, based on this equation here, the amount of products you're going to get, in this case, the amount of complete meals, would be 8 packaged meals, right? And that's a maximum amount of meals you can get from the combination that is given here, right? So the cookies would be the limiting reactant, and the other items, which are not completely used up, would be regarded as the excess reactants, all right? So this is basically an illustration as to how the whole limiting reactant concept works. Okay, so now we're gonna move to a chemistry example. Oh, actually another example based on the previous example. So let me just write a little equation up top here, just to remind ourselves of the combination. It is 1 sandwich, I'm going to use SA to represent sandwich, plus 2 cookies, I'm going to use CK to represent cookies, plus, what's the other item? Orange. I'm going to use OR, let me see here, plus 1 orange. I'm going to use OR to represent orange, and I'm going to use CM to represent complete meal, all right? So that's the equation we're working with. So here we have a question. How many meals can be made from 105 sandwiches, 202 cookies, and 107 oranges? So the way you'd go about solving this is you start off with the 105 sandwiches, and then you represent in this conversion factor here the relationship between the complete meal and the sandwich. So 1 complete meal divided by 1 sandwich would be that conversion factor. So therefore you're going to end up with 105 sandwiches based on the original 105 sandwiches. Okay, then we have 202 cookies. According to the relationship established by the equation, 1 complete meal divided by 2 cookies would be the ratio. So therefore this is going to give you 101 sandwiches. Oh, my bad, this should be complete meal right here. So this should be 101 complete meals for the 202 cookies. And then finally, 107 oranges, I would multiply that by 1 complete meal divided by 1 orange. So that will give you 107 complete meals, right? So to figure out how many meals can be made, the answer would be this right here, 101 complete meals, CM, all right? And that's because based on the calculations that we did for each of these, this is the lowest of these 3. So therefore, the cookies again in this case would be the limiting reactant, all right? So that's another non-chemistry example illustrating the whole limiting reactant idea and how you can determine how much product you expect to get based on the limiting reactant. So the key thing you need to remember here is that the limiting reactant, as the name suggests, limits the amount of product you expect to get. You cannot get any more product out of a reaction or out of this combination in this example without determining or knowing what a limiting item is, because that is the item or that is a reactant that determines how much product you'd expect to get. All right. Okay. Any questions about the limiting reactant concept in this non-chemistry example?
No.
Okay. So let me just go to this example here. So this question said magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. So the A part says how many grams of magnesium nitride can be made in the reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen, and B, how many grams of the excess reactant remain after the reaction? Okay, I'm going to just aside for a minute. I want you to read this question and think about it, and when I get back, shouldn't take long, I want you to tell me how you go about solving this problem. I'll be right back. Oh. Okay, folks, I'm back. So, what would be the very first step in order to solve this problem? I'm going to make this smaller so I have more space to write.
Figuring out how many grams of magnesium and nitrogen it takes to make 1 gram of magnesium nitride.
Nope, that's not the first step. Anybody else? What would be the very first step? You won't be able to proceed without doing this particular first step.
Is it like figuring out how much can be formed to make like the complete magnesium nitride, like how we did for the last example?
Yeah, but before that, I mean, you're right, but there's an important step you have to take before even that. You cannot proceed without doing this first step. Let me give you a hint. You have to write a what?
Formula?
Well, not just a formula. You have to write down a what? Or you have to figure
Conversion?
out a balanced equation. All right? You cannot, for any stoichiometric type problem, you cannot solve it without figuring out the balanced equation, because the balanced equation will give you the mole ratios that you're going to need. All right? Okay, so we have some information given here. It says that magnesium nitride can be formed from the reaction of magnesium metal and nitrogen gas. All right? So what would be the reactants in this? What would be the formula for the reactants in this particular problem?
Magnesium plus nitrogen equals magnesium nitride.
Okay, so the formula of magnesium is what? What's the formula of magnesium?
Mg?
Mg. And what's the formula of nitrogen?
N.
N2. Remember, nitrogen is one of 7 elements that exist as diatomic molecules, right? You have hydrogen, you have oxygen, you have nitrogen, you have, what's the other one? Fluorine, bromine, iodine, chlorine. These elements exist in nature as diatomic molecules. So you need to remember that, all right? So you can't just put N for the formula of nitrogen in this reaction. You have to put N2, all right? Okay, so those are the reactants. What would be the formula of the product? And it's only one product, magnesium nitride. So what's the formula for magnesium nitride?
MgNO3 and then 2.
Nope. Anybody else can come up with a formula for magnesium nitride? Okay, let me give you a little hint. Let me get out of this for the time being.
Mg3N2.
Very good. Okay, thank you. So the formula for, whoops, go back to here. The formula for magnesium nitride is Mg3N2, right? You have to figure out the formula for compounds such as magnesium nitride so as to get the right formula. Okay, so what we have here is an unbalanced equation. So the next step is that we have to balance it. So how would you balance this equation?
You need a 3 in front of magnesium.
Put a 3 in front of the magnesium. Very good. Okay. And I don't think you need to make any changes because you have 2 nitrogens here, 2 nitrogens here. So everything is balanced. All right. So now we can get into the A part of the question, which says, how many grams of magnesium nitride can be made from the reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen? So what I'm going to do is start off with the 35.00 grams of magnesium. I'm going to convert that to moles. So I'm going to have 1 mole of magnesium above. And the molar mass, if I'm not mistaken, let me see if I can find my periodic table. I think it's 24.31, but where is my periodic table? I can't seem to find it here. So that means I'm going to go to Canvas. Where is Canvas? Where is Canvas? Okay, files, tables, chemistry, download, bring that up. Okay, so magnesium has a molar mass of 24.30. Okay, I was almost right. Oh, what am I doing? Okay, so this is 24.30 grams of magnesium. And then the next step would be the mole fraction or the mole ratio between the magnesium and the product. And based on the numbers here, and 1 would be here. So you're going to have 1 mole of Mg3N2. And down below, you're going to have 3 moles of Mg. All right. So this will cancel with this. This will cancel with that. So let's work this out. 35 divided by 24.30 times, or I should say divide by 3. So according to my calculations, this works out to be equal to 0.4801. 4801 Mg3N2, all right? And then I'm going to do a similar calculation for the nitrogen, starting off with 15.00 grams of nitrogen. Convert that to moles. So you're going to have 1 mole of N2. Down here, you're going to have 28.02 grams of N2. And then the mole ratio, which would be between the nitrogen and the magnesium nitride, 1 mole of Mg3N2. Down here, you're going to have 1 mole of N2. So let me work this out. 15 divided by 28.02 times 1 gives you, according to my calculation, 5353. And this would be moles of Mg3N2. And this should be moles here as well. All right? Okay, so we compare these two numbers here, and the one that is lower in value would be the 0.4801, right? So that tells us that this here, the magnesium, is the limiting reactant. And that tells us also that this would be the excess reactant, all right? So to answer the A part, all we have to do is convert the 0.4801 grams of Mg3N2 to, this should be moles actually, convert the moles of magnesium nitride to grams. So we're gonna have 1 mole of Mg3N2, and up here, we're gonna have the molar mass. So I'm going to do a bit of cheating here because I'm going to go to, okay, what's going on here? I'm going to go to a particular website which allows us to calculate, it's called the molar mass calculator. Okay, so the formula is Mg3N2, all right? And I hit calculate, and according to this, it's 100.93. So I'm going to go back here, and I'm going to put 100.93, let me do this first, right here. So 100.93 grams of Mg3N2. So I'm going to work this out, 0.4801 times 100.93, and the answer would be equal to 48.56 grams, 48.56 grams of Mg3N2, all right? And that's basically how you would solve the A part, all right? Any questions about this? Any questions? Okay, now the B part is a bit more complex because the B part is asking how many grams of the excess reactant remain after the reaction. Now remember I said that based on what we have done before, we determined that the limiting reactant is the magnesium, which means that the excess reactant is the nitrogen. So what this question is asking is how many grams of the nitrogen, let me put nitrogen here, the excess reactant, oops, the excess reactant is nitrogen. How many grams of nitrogen remain after the reaction? Okay, so how are we gonna do this? Let me get out of this here and go to my writing pad here. And I'm going to just eliminate all of that there. Okay, so what we're going to do is first start off with the limiting reactant, which is the 35.00 grams of magnesium, right? Then we have to convert that to moles, which I think we did before. 1 mole of magnesium over the 24.30 grams of magnesium, all right? The next step is to determine how much of the other reactant reacted, which would be the nitrogen. Now, based on the equation that we have here, right, that we started off with here, there's a 3-to-1 mole ratio between the magnesium and the nitrogen. So the way I'm going to represent that here is that I'm going to put 3 moles of magnesium, I'm sorry, 3 moles of magnesium down here. And what was it? Let me refresh my memory. 1 mole of nitrogen above, right? So one mole of nitrogen up here, all right? And then the next step would be to convert the moles of nitrogen to grams. So you're gonna have 1 mole of nitrogen down here, and then the molar mass of nitrogen, which is 28.02 grams of N2, all right? So we work that out, 35 divided by 24.30 divided by 3 times 28.02, and I got as the answer 13.45 grams of nitrogen, N. I should put N here. N2, I'm sorry, N2 here, okay. So this represents, and please note, this represents the amount of nitrogen that reacted, all right? But the question is asking for the amount of nitrogen that remains. So the amount of nitrogen remaining would be equal to the amount of nitrogen that you started off with, which is the 15.00 grams, minus the amount of nitrogen that reacted, which is the 13.45 grams, and that gives you, according to my calculations, 1.55 grams of nitrogen. So that's basically how you'd solve this problem. And this is a typical stoichiometric type problem where you have to find out which is the limiting reactant and which is the excess reactant and so on. All right? Any questions about this? Any questions? Okay, so if there are no questions about this one, let's move along. Okay, so the next topic we're going to talk about, and I think this is going to be the last topic for today, we're going to talk about reaction yields. Very important concept as well. If you look in any chemistry journal where you have reported, compounds being produced and so on, what you'll find in each of these journals where this happens is a quotation of the percent yield of the particular reaction. So this is basically a routine thing that is done, and it's used as a measure of how successful the reaction is, all right? So let's talk about the difference between, firstly, the theoretical yield and the actual yield. Now, the theoretical yield is basically the amount of product that you'd expect to get if the reaction worked perfectly, right? If you were living in a perfect world, then the amount of product that you get in a reaction, that would be what we call the theoretical yield, right? And in fact, in the previous example that we looked at, we actually calculated the theoretical yield. Let me show you. The theoretical yield that we calculated was right here, the 48.56 grams of the magnesium nitride. This is what you'd expect to get if everything worked well, all right? So that's the theoretical yield, right? Now, the actual yield, as the name suggests, is basically the amount of product that you get if you did the experiment and you get the product and you weigh it, right? So you're not calculating this value. You basically did the experiment at the right amounts of each reactant together, and then whatever the conditions are needed, you apply those conditions, you get your product, and you isolate it and you weigh it. That would be your actual yield, right? Now, of course, we do not live in a perfect world. So therefore, the actual yield, more likely than not, will be less than the theoretical yield, okay? So this leads us now to what is called, before we get to the percent yield, one might be wondering, why is it that the actual yield is less than the theoretical yield? And there are several reasons why. There could be errors on the part of the experimenter, poor techniques. But I would say the major reasons, there are two major reasons why. Even if you did everything correctly and so on, there are two major reasons why the actual yield would be less than the theoretical yield. One would be that in some cases, the reactions are reversible. In other words, as soon as the products are formed, then the products themselves react to form the reactants, right? So that could cut down on your yield, right? Another reason is that the product themselves are reactive. So therefore, as soon as the products are formed, then the products themselves react, okay? And you can try to counter that by, applying conditions which would not allow the products to react, but sometimes you simply cannot avoid it. And there's a third reason why the actual yield would be less than the theoretical yield, and that has to do with what we call competing reactions. In other words, if you add two reactants or more reactants together, they can react to form more than one product in some cases, and this is particularly true in organic reactions. And that, again, will cut down the yield of the product that you're actually focusing on. So, there are several reasons why, the world doesn't work, the reaction doesn't work the way that you want it to get the maximum amount of product possible. Okay, so with that said, let's talk about percent yield, which is basically, as I said before, what is used to indicate how successful the reaction is in terms of getting as much of a product as you can. And here is basically how you calculate the percent yield. It's the actual yield divided by the theoretical yield times 100%, all right? So percent yield, of course, is expressed as a percentage. And of course, that percentage would have to be either equal to 100% or less. You cannot have a percent yield which is greater than 100%, all right? Okay, I think I'm going to stop here for today because I don't want to start this particular topic and stop in the middle of it. So that's it for today. Let me remind you about the quiz, which is due tomorrow. All right, so make sure that it is submitted by then. If you have any questions about it, feel free to contact me via Skype. I will be available today from what time? From 1 to 5 p.m. today. All right. So please, please, please come and see me, or come to Skype and see me if you have any problems that you're facing with the quiz that I've given you. All right. Are there any questions, general questions about you know, the course, whatever? Okay, so if there are no questions, that's basically it for today. So enjoy your weekend, and I'll see you guys on Tuesday. All right, so take care.